Hello everyone, welcome to today's webinar titled Algorithm to Implementation, Combining MATLAB and Simulink with PSpice to Streamline PCB Design. My name is Kishore Kanani and I'm from Cadence Design Systems. With me I also have Corey Mathis, who will be the co-presenter of this webinar, and he's from Mathworks. As well as we also have Alok Tripathi from Cadence Design Systems, who will be actually demoing some of the products later in the webinar. So let's talk about what is this Cadence and Mathworks partnership. So basically Cadence and Mathworks have partnered to provide system level simulation for IoTs, medical devices, automotive, or any of those system level products. In this case, you can actually do the electronic circuits designed in PSpice, electromechanical and behavior models you can simulate in Simulink. So why is this partnership? Is because prior to this integrated solution, customers used to simulate their design blocks independently. There was no feedback from one system into the other. So there was a lot of manual effort for running simulations in both of those simulations environments separately, and then you had to bring them together. So it was a very time-consuming and error-prone design environment. What we have put together is a co-simulation environment for system-level simulations in a much faster, integrated, and less error-prone process. So now you have the analysis capabilities for IoT type of designs, automotives, for customers who are concerned about reliability, cost, productivity, manufacturability, etc., etc. Today's agenda for this presentation will be, we'll start off by talking about some of the challenges in PCB design, then we'll introduce you the new systems, PSpice systems option, and then we'll summarize. Let's start off the webinar with talking about challenges in PCB design, and I'll start off by handing it over to Corey Mathis from Mathworks, who will get into this topic. Here we go, Corey.
Thank you, Kishore, for the introduction. I'm very happy to participate in today's webinar. Let me first start by talking a little bit about some of the challenges we see our customers having in creating a streamlined PCB workflow. First, designing a PCB is not all that different than designing any other complex system. First, we start with our specification, which in general seems to be getting more and more strict for new low-cost, low-power designs. Next, we partition the pieces of our designs to the various engineering teams, who still tend to either be analog-focused or specializing in digital design. Next, we integrate the actual hardware, which could include surface mount components, custom circuits, as well as FPGAs and SoCs, and we try to test and verify that everything is working as expected before we send off our design to be fabricated. Well, that sounds straightforward, but in reality, it is not usually the case. What we typically see today is that verification is heavily isolated from the original system specification and design. We also see that the design teams continue to be disconnected, making it very difficult to abstract out portions of the design and to make trade-offs between what is done in the digital domain versus what is done in the analog domain. This can be due in large part to the fact that simulating analog and digital together is challenging and time-consuming, and ultimately all of this leads to slow design iterations. Mathworks' solution for many of these challenges is model-based design. Model-based design is a methodology that streamlines taking requirements through system exploration and design all the way to implementation and verification. At Mathworks, our model-based design environment is Simulink, which is a graphical time domain design and simulation platform. In Simulink, your system requirements can be translated into models which serve as an executable specification. The models can include continuous time, or analog models, combined with discrete time, or digital models. While Simulink is a time domain design environment, it supports event-based driven simulation with control via advanced state machines, and modeling at various levels of abstraction using both mathematical and detailed physical layer models, as well as also allows for the inclusion of various test bench components, including environment and channel models. Lastly, model-based design, or MBD, supports in many cases translating a system model into an implementation model through code generation, either in the form of C or C++ code or even HDL. And of course, we need to test and verify to make sure the implementation spec matches our executable specification. If we look at how model-based design can be used in a PCB workflow, there are a lot of similarities. In general, most PCB workflows do have some aspect of a top-down design, where we start with a system model, which we then elaborate on to add impairments such as circuit level or fixed point effects. But in order to have an efficient workflow for PCB design, we need to have an environment that has the right level of performance, has the right models available, and also allows an easy bridge between system design and circuit level implementation. In working with Cadence, what we have done is to create this bridge using PSpice system option, which Kishore will talk more about in just a few minutes. But before we do that, let me walk through this workflow using an example. In this example, we have a Simulink design which is an example of a motor control system. It has both continuous time and discrete time components, physical and electrical domain models, as well as environmental models that allow us to make trade-offs on performance of loading effects. In Simulink, there are a wealth of visualization capabilities to look at time and frequency domain waveforms, Bode plots, virtually any mathematical representation of the data. What we see here is that our very first simulation with an ideal load gives us pretty optimal results. What we can then do next is elaborate on the design and add a non-ideal load, which also takes into account vibration effects, to see how this changes our system level performance. But at some point, we need to go off and design some of the components of the system. Here, we are using OrCAD and PSpice to design and simulate the inverter at the transistor level. What we then want to do is take this detailed level design and plug it back into our system simulation to see how the results change. So to accomplish this, PSpice system option supports co-simulation between Simulink and PSpice, allowing you to integrate your detailed level implementation with your system level test bench. And as we can see here, the results change when we add the electrical effects of the designed inverter. The design may still meet specification, but it is critical to know how the overall margin and performance is affected. So in summary, Mathworks and Cadence are working very closely together to bridge system-level simulation in MATLAB and Simulink with implementation and detailed design in PSpice, streamlining a model-based approach for PCB designers. To show you more about the exact features and capabilities, let me turn it back over to Kishore.
Thanks, Corey. Mathworks and PSpice integration now enables system-level simulations. Customers can now simulate the entire system-level design with an integrated MATLAB, Simulink, and PSpice debug environment. Like I mentioned earlier, prior to this integration, customers used to simulate their design blocks independently without being able to input the feedback of one system into the other. Customers can now easily simulate electrical circuits with electromechanical as well as algorithmic blocks all together in one simulation run. Let me introduce our latest product for system-level simulation on the board side. It's called PSpice Systems Option. It includes 4 key technologies. The first one is PSpice MATLAB Visualization Interface. Designers can now leverage MATLAB visualization capabilities for post-processing of PSpice data. In other words, you can take any PSpice data into MATLAB and visualize the data in the MATLAB environment. I will show you some of these examples in the upcoming slides. The second one is evaluate MATLAB functions in PSpice. In other words, designers can also enable MATLAB computations in the PSpice analysis. This brings the entire MATLAB function library into PSpice. Thirdly, we talk about Simulink and PSpice co-simulation interface. So Cadence and Mathworks have enhanced this integration to provide a flow where customers can import a PSpice model in Simulink and co-simulate as well as utilize all the MATLAB analyses and measurement functions. Lastly, designers can also import MATLAB modules as simulation model in a PSpice environment using PSpice DMI functionality. So let's talk about some of these in detail. This slide shows you how you can leverage the MATLAB visualization capability from PSpice. In other words, you can import a PSpice waveform data into MATLAB and visualize the same data in the MATLAB environment in a different form like a polar plot. You can also evaluate the comprehensive MATLAB functions in PSpice measurements or the PSpice models. So let's talk about some of the capabilities that are available with this integration. For example, you can visualize different types of plots in MATLAB. You can actually take the data and visualize the data in a polar plot, 3D plot, or a Nyquist plot. Users also have a complete and seamless access to the MATLAB plotting capabilities. You can export the PSpice simulation results into MATLAB with a single click. You can customize the waveform processing while you're exporting. You can even run your own MATLAB scripts on the exported data. We have also extended the PSpice waveform analysis capabilities so that if you're viewing any kind of data in the frequency domain analysis, you can take that data into the MATLAB environment and visualize that in a polar plot. Or if you're doing a transient and a DC sweep analysis, you can also visualize that data in a 3D format in MATLAB. In other words, let's talk about how simple it is to view the data in MATLAB. You select the mode. In this case, you want to export all the traces. You select the traces. In this case, you can select all traces or specific traces. Now, once you have selected the traces, you can view the data in MATLAB. And at this point, you can also configure MATLAB script. So if you want to run any of the custom scripts, you can also view the custom scripts. In this example, we are showing how you can draw a polar plot on the transient analysis running in PSpice. So in other words, on the left-hand side, you're seeing a transient analysis waveform in PSpice. And on the right-hand side, we are showing how you can view the same data in a polar plot in MATLAB environment. Next example is more on the frequency analysis side. So if you're running an AC analysis in PSpice, you can view the same results in MATLAB as a polar plot. Here's another example. So you can take any of those data of transient or AC analysis into MATLAB and view it in a different format. So this example shows you how you can plot multiple BH loops with a variation against air gap or a DC bias voltage. So example over here shows you on the left-hand side is a run in PSpice with a single BH loop, or you can view the same results with a 3D view over here, varying gap equals to 0, gap equals to 5 mil, or gap equals to 10 mil. Also, in addition, if you want to perform a DC sweep analysis of a drain current versus a drain to source voltage of any of the MOSFETs while varying temperature, you can visualize the data in PSpice, or you can even export the data into MATLAB and view the data in 3D. So this curve shows you the drain current versus the voltage across drain to source varying at different temperatures. The next what we will like to show you is how you can evaluate MATLAB functions in PSpice. In other words, you have access to all MATLAB mathematical functions like rise time, peak to RMS, peak to peak, or any other complex MATLAB function can now be analyzed in PSpice. Also, you can include MATLAB functions in control sources like in the Allegro Design Entry HTL solution or the ORCAD capture. In other words, we support both design entry solutions, Allegro Design Entry HTL, as well as the ORCAD capture. Next, let's talk about the MATLAB Simulink PSpice Code Simulation interface. Code Simulation combines three best-in-class simulation tools to provide unmatched design simulation environment for electrical as well as physical systems all together in one integrated environment. For example, PSpice, MATLAB, and Simulink. PSpice, as you all know, is a full-featured analog mixed signal simulator with support for digital elements to help you solve virtually any design challenge. MATLAB is the language and environment for technical computing. And Simulink provides you a platform for multi-domain simulation and model-based design of dynamic systems. So let's look at an example of a field-oriented control of a permanent magnet synchron machine. This control technique is very common in a motor drive system for hybrid electric vehicles, manufacturing machinery, as well as industrial automation. This kind of technique is also common in washing machines. In other words, you have a field-oriented controller with a PWM, which could be in the digital domain. You have a power inverter, which could be an analog block, or you could have some sort of an electromechanical motor. All of this needs to be simulated in one integrated environment. So what are some of the co-simulation benefits? You can co-simulate electrical, mechanical, as well as a system level block in one integrated environment. You can simulate with ideal models for faster simulation, or you can simulate with actual electrical designs using PSpice models for more accuracy. The electrical simulations of the PSpice model exhibit all the nonlinearities, the delays, as well as all the real-world effects. So this integration provides you full access to PSpice and MATLAB environments for in-depth design and debugging, as well as visualizing the data in the environment that you are most comfortable in. So this is a detail level brush DC motor co-simulation example. So at our top, what we are showing you is a motor model with a fan load designed in Simulink. You can descend into it and look at the multiple different abstraction levels. And on the left-hand side, what we are showing you is a driver circuit model designed in PSpice. So what we are showing here is a motor model is designed in Simulink, and the driver circuitry is designed in PSpice. And what we are showing you is with using the PSpice systems options, you can co-simulate them both together. At a high level, the user flow is you can start off, the initial block implementation is done in Simulink. Then you go into the electronic side, you're designing your electrical circuitry. You can do that in PSpice. You can implement that in PSpice. Then you can integrate these together using the PSpice systems options, and then fine-tune your design using various operating conditions. So very simple integrated environment by starting off in Simulink, going into bringing the model of PSpice in there, and then integrating them together and then co-simulating. At this point, I will turn it over to Alok Tripathi, who will demonstrate 3 different demonstrations to you. The first one will be the visualization interface. In this one, he will show you how you can take the PSpice data and visualize that in the MATLAB environment. The second one here, he will show you how you can run MATLAB functions in PSpice. And third one will be the co-simulation between Simulink and PSpice. That being said, here you go, Alok.
Thanks, Kishore. My name is Alok Tripathi, and I'm the product engineer for PSpice and OrCAD products. Now I'm going to show you a demo of PSpice Simulink co-simulation. One of the key advantages of co-simulation is its ability to simulate a heterogeneous model developed separately but coupled for co-simulation, thus allowing the study of a complete system, which otherwise would not have been possible. To demonstrate this, I'll have an example of solar microgrid inverter. The key block of the systems are PV cell, DC to DC converter, DC to AC inverter. Here's the system architecture of this design. We will leverage MATLAB capabilities to model PV cell, irradiance, and develop electronic circuit in PSpice. And then we'll connect these diverse modules together to simulate complete system using PSpice system option. There are various building blocks of the system. We'll start our design with OrCAD Capture for circuit design, and as you can see, we could replicate exact architecture here as is. This improves the traceability and debuggability of the design. OrCAD Captures enable you to capture your simulation design in a flat or hierarchical manner. By using hierarchical design, we can design and optimize individual block independently and connect them together. So this is kind of bottom-up design approach. This also enables team design and concurrent design, where teams are working on respective modules parallelly. Let's look at the different blocks of this design. This is the front end of DC to DC converter. It will take unregulated DC input voltage and deliver regulated DC for next stage. Input to this block would be driven from PV cell model in MATLAB. Gate drive and feedback control is also captured in this block itself. Let's move to the next block. Next block is DC to AC 60 Hz inverter circuit. Its output should be 100 volt or 110 volt 60 Hz sine wave. Inverter control and gate drive has been captured in a separate block for inverter. Now let's simulate and see if we are getting desired result. Once inverter output is stabilized, it is connected to output terminal of this circuit. And as you can see, results seems to be looking pretty good. Now let's go to MATLAB and see how can we bring in this electrical circuit in MATLAB and connect it with the rest of the PV cell circuit captured in MATLAB. In MATLAB we have PV cell design ready. To bring PSpice circuit here, place PSpice block from a library browser. Once you have PSpice system option installed, you should be able to see this in Simulink library browser. Double click on this option to open co-simulation setup form. Browse and point to your OrCAD capture PSpice project. Once you have done this, you should be able to see all simulation profiles from your electrical circuit in this form. Configure input and output nodes to complete linking these two MATLAB and PSpice modules together. As you can see, in few mouse clicks, you can interconnect these two systems and we are ready for complete system level simulation. Configure input and output nodes to complete linking these two MATLAB and PSpice modules together. As you can see, in few mouse clicks, you can interconnect these two systems and we are ready for complete system level simulation. In this case, input to PSpice block is PV cell DC output voltage, which will drive front-end DC to DC boost converter, and output from PSpice is inverter output. We have connected a true RMS meter and total harmonic distortion meter to measure the quality of output sinusoidal wave. Let's run the simulation now and look at the result. The top two waveforms represents the variation in irradiance and environment temperature. These are two important factors impacting PV cell DC output. The other two scope represent the PV cell DC output, which is unregulated, and inverter output from PSpice. As you can see, the inverter output from PSpice is looking pretty good, and we can also see in MATLAB that we are getting 110 volt true RMS and the sine wave with the harmonic distortion is less than 1%. Now let's try to change the implementation to actual semiconductor devices. We'll go back in Capture and quickly change the implementation to a different schematic. These circuits are same as the previous one, except now these uses semiconductor devices, MOSFET and IGBT instead of ideal switches. Let's run the simulation again and to see if anything has changed. As you can see, output voltage has indeed changed. This shows your system behavior can change when you move from ideal device to actual semiconductor model, and how you can leverage PSpice system option to catch such changes in design stage itself without having a need to build an actual prototype. In this demo, we have seen how easy it is to connect and simulate very diverse type of modules together and simulate complete system. This not only reduces the time to market, but also reduces the number of prototypes required. Let's have a look on use of MATLAB functions inside the PSpice. PSpice systems options enable you to use MATLAB function during post-processing and during simulation. One can use both custom or MATLAB standard functions. Using this capability, one can model a device using MATLAB function or use MATLAB function in measurement expressions during waveform analysis inside the PSpice. Let's see a demo of these two capabilities. We'll first focus on use of MATLAB function on modeling a device. You can use PSpice behavioral devices and use MATLAB function in expressions. One can use a function with any number of arguments. Let's start with a simple case. Assuming I want to model a current source whose output is defined as a sine of input voltage in degrees and not in radians. This sine function may not be readily available as supported function in Spice. However, it is a standard function in MATLAB. To use this MATLAB function in PSpice with the rest of electronics, I can just place a behavioral device symbol and define its expression to use this function construct MATLAB function and provide inputs to this. The first argument here should be your MATLAB function name, which would be sine d in our case, and then we should define arguments required by this MATLAB function. The last argument here need to be the number of arguments required by MATLAB function. In this case, it would be 1. And with this simple steps, we are done with our model definition to use MATLAB function inside the PSpice simulation. Now let's see another example. Here, my goal is to detect a window where my power converter is operating in third quadrant. In other words, this is the case where an electromechanical system is operating in a reverse motoring mode. One need to develop a circuit to detect this mode of operation in the PSpice. However, it would be easily possible to do this mathematically in MATLAB. I can write a custom MATLAB function for this and use that in PSpice. To do this, I'll use MATLAB custom function phase 3q. This function is written in MATLAB script. Phase 3q function need two inputs, voltage waveform and current waveform. Expected output from this function is positive waveform pulse where third quadrant mode of operation is detected. Here is my circuit to use this function. I have connected a voltage and current and my load is inductive in nature. Now let's run simulation on this. Here are the simulation results. The top plot pane results simulation from first model where output current is sine d of input voltage. As you can see, results are on expected lines. Bottom plot pane represents the simulation result from second model where goal was to detect third quadrant mode of operation. In the third quadrant mode, both voltage and current would be negative, so one can expect output voltage to be high when this mode is detected. Here also the results are on expected line. The green color pulse shape waveform represents the output of a MATLAB custom function block. As you can see, that it accurately detects the third quadrant mode of operation from my voltage and current waveform. One can use this output in power controllers for further processing. Now let's see how can we change the MATLAB function during the analysis phase and see the effect of updated function in simulation. Say we want to change the output signal voltage level to be 5 volt instead of 2 volt. I'll go to MATLAB, update my script, save the script, and can come back to PSpice and run this simulation again. And we can see the effect of this change. Now my output voltage is 5 volts. So we have seen how easy it is to use MATLAB function inside PSpice for developing a complex mathematical model using MATLAB and connecting that in a seamless manner inside PSpice with rest of your circuit. You can do this just like use any other Spice model. This brings the power of two best-in-class tools together and provides unmatched design and simulation capabilities. Now let's take a look at demo of using MATLAB function in PSpice waveform analysis. PSpice evaluate measurement dialog has been enhanced to include two new measurement functions. These new functions are named as MATLAB function 1 and MATLAB function 2. Using these functions, one can use any MATLAB function while evaluating measurements in PSpice. Let's have a look how this works. Here's the simple DC to DC converter. Input to this converter is a full bridge rectifier with a capacitive filter circuit. We will simulate this design and see the voltage and current waveforms at various nodes, namely input AC voltage, source current, and output DC voltage. Now we would like to measure total harmonic distortion of input current waveform and peak-to-peak ripple in output voltage. We'll use MATLAB function THD and peak-to-peak for this. We'll first measure peak-to-peak voltage on rectified DC. peak-to-peak measurement will give us ripple voltage. To do this, let's bring up evaluate measurement form in PSpice. Select measurement named MATLAB function 1. Provide the name of trace on which you would like to run this function. This would be Vout. Next argument is MATLAB function we want to use. This will be peak to peak in our case. This will evaluate MATLAB function peak to peak on voltage waveform at node Vout. To perform this evaluation, PSpice have invoked MATLAB in background, passed complete waveform and request MATLAB to perform peak to peak function evaluation. The result of this function evaluation done by MATLAB has been displayed in PSpice. And all of this is done right from PSpice environment. Similarly, we can evaluate another measurement THD, total harmonic distortion, on source current. We can use standard measurement functions or any custom function developed using MATLAB script in this flow. This new functionality enables us to leverage mathematical computation, capability of MATLAB on PSpice simulation result in seamless manner right from a PSpice environment. Now I hand over to Corey. He will demonstrate how to generate PSpice models directly from MATLAB.
Thanks, Alok. The last capability included in PSpice Systems option is some functionality that Mathworks has developed jointly with Cadence to export models from MATLAB and Simulink for use in PSpice. The interface that enables this is the Device Modeling Interface, or DMI. DMI allows you to simulate various types of behavioral models directly in PSpice. In working with Cadence, we have created the capability to export both MATLAB models and Simulink models using DMI. The workflow for doing this is straightforward. In Simulink, we can generate ANSI C code for many of the native Simulink blocks, as well as embedded MATLAB code using the MATLAB function block. We then use a special PSpice target for embedded coder that customizes the C code for the device modeling interface. Once we have the customized C code, we can then compile it into a DLL and a library object and bring those into PSpice and create a new native object file and symbol view. Let me switch over to an example to show you exactly how this works. Okay, this is the Simulink environment. If you're new to Simulink, it differs from MATLAB in that it's a graphical time domain environment with many different libraries for designing all sorts of different complex systems, whether those systems are communication systems, DSP related, or true mixed signal systems. The example that I'm going to use today to show model export to PSpice comes from our mixed signal library, which is available for download on mathworks.com. In this example, I have a behavioral operational amplifier, which is built using high-level Laplace and mathematical models. Note, however, that I'm using some circuit elements to control the biasing and the loading of the operational amplifier. While Simulink is not a SPICE simulator, it does allow for the inclusion of circuit-like parasitics, including impedance mismatch, reflections, and viswar. This allows us to create a more accurate behavioral model of the op-amp, and that really is the goal, to create a fast behavioral model. If I click the Simulate button, what you'll notice is that this executes very fast, essentially instantaneous. But again, this is a fairly basic model. As model complexity increases, so will simulation time. But let's assume that this model represents the actual op-amp that I want to use in my board design. What I might want to do is connect this fast behavioral model to other circuit elements that live in ORCAD or Allegro. In order to do this, we use code generation and export the model into a format that DMI can understand. The tools required for Mathworks to do this is our embedded coder. Embedded Coder allows us to customize ANSI C code for a particular target or application. In this case, we will customize C code for PSpice DMI. The output of code generation will be two files, the compiled C code in the form of a DLL and a library component which will be required by PSpice to import the model. What Mathworks has done is to automate many of the steps to creating this target using a pilot support package, which automatically customizes embedded coder for PSpice DMI. All you have to do is load the target, which can be seen here, and all of the settings for embedded coder will be loaded automatically. Access to the pilot support package is free. You simply need to contact your local Mathworks representative. After loading the PSpice target, I can then simply go to Code, C++, and select Build the Model. As previously mentioned, there are two files that will be created in your Simulink directory. These are the compiled C code in the form of a DLL, as well as this library component, which will be required by PSpice to import the model. With these two files, you've now created a completely portable model that can run outside of the Mathworks environment. So now let's go to OrCAD and load our component into PSpice. The first thing I need to do in PSpice is I need to create a custom library for PSpice from the model that came from Simulink. I can do this using the PSpice model editor. In the PSpice model editor, I can export a library to my parts library. To do this, I give the model editor the library file that came out of Simulink, and then I can create a new part library for capture. This file will be an OLB file, and it can be added to my design by going to Library, Add File. I simply need to scroll to the output of the model editor. Once I've created this new library, in my design and schematic capture, this will now show up as a new part that I can use in any of my designs, and can be picked and placed from the schematic capture. So I've already done this and have recreated the test bench for the op-amp design that came out of Simulink. So if I simulate this design, what I would expect to see is the same results as I saw that I had in Simulink. And the reason being is we've essentially just converted our Simulink design into a different format. We've converted it into C code, a form of C code that PSpice can understand, and brought that into the PSpice environment. So when we compare the two waveforms, we can see that they are identical. We can also see that the runtime performance of the models are very similar. They execute, again, almost simultaneously. And the reason, again, is these are behavioral models, which is really the function. There are two caveats to be aware of with this flow. The first is that any of the components that you are using in MATLAB or Simulink need to support C code generation. The vast majority of components in Simulink do support C code generation, as does the good majority of the MATLAB language. The second thing to be aware of is that when you generate code, you need to configure the code to generate at a time step that is fine enough to capture any analog behavior of your design. So in this case, I'm generating my model with a time step in nanoseconds. You want to make sure that you're capturing the actual analog behavior of your design when you generate the C code. And that's crucial to have good correlation when you bring in this behavioral model into the PSpice environment. So now, let me go back to a couple slides just to summarize what we've seen. Cadence and Mathworks are partnering together in order to connect system design and physical implementation, in this case specifically for PCB design. The goal is to provide more integrated workflows which are crucial for low cost, low power requirements seen in IoT, in medical, and in automotive. By partnering together, we believe that we can provide a complete platform for PCB design, which will increase productivity by reducing the number of design iterations for our joint customers. PSpice System Option accomplishes this by providing a direct interface for MATLAB, both by integrating MATLAB functions directly into PSpice, as well as using MATLAB for simulation analysis and visualization. PSpice Systems Option also includes a co-simulation interface with Simulink for unit verification testing, as well as the export of MATLAB and Simulink models to PSpice through the DMI interface. For more information on any of these features, please feel free to contact myself, Corey Mathis at Mathworks, or Kishore, or a look at Cadence. Thank you so much for listening.